Today's notes are all about how we classify numbers, the names that we give to different numbers. We are talking about the real number system, and each of these terms is a specific type of number. So we have what are called natural numbers, and we'll talk about those here in a little bit. Every single natural number, notice, is inside the whole number circle. So every natural number is a whole number, but there are some whole numbers that are not natural numbers, and so on. Every natural number and every whole number is an integer, but there are some integers that are neither whole numbers nor natural numbers, and so on. We also have something called irrational numbers down here at the bottom, and we'll talk about what each of these terms means here shortly. So as it says here, the set of real numbers consists of both the rational and the irrational numbers. So every single number is either rational, it either belongs in this big circle up here, the target, or it's irrational, which is down here, the base. Every number belongs to one of those things. Now, if it's a rational number, it could further be classified as an integer or a whole number or a natural number. If it's irrational, it's only irrational. It can't be any of those other things. So the first type of numbers we're talking about are what are called natural numbers. These are also known as counting numbers. Natural numbers are the positive counting numbers. Really, when you count, if it's a number that you would count to, it is considered a natural number. So 1, 2, 3, 4, 5, 6, 7, 8, all the way up. 101 is a natural number. 9,421,358,943 would be an example of a natural number. Might take a while to count there, but I suppose you could. All of those are natural numbers. Whole numbers are all of the natural numbers plus 0. So all of the natural numbers, 1, 2, 3, 4, 5 on up, those are all whole numbers. 0 is also a whole number. So 0, 1, 2, 3, 4, 5, and so on. Notice we don't have any negative numbers. Negative numbers are not considered whole numbers. We also don't have any fractions. 1/2 is not a whole number. So it is the counting numbers, the natural numbers, plus 0. The next layer that we have is what is called integers. Integers are all of the whole numbers, so 0, 1, 2, 3, 4, 5 on up, plus their opposites, so the negatives. So positive, negative whole numbers, including 0. 0 is a whole number. So we have all of the positive whole numbers. Then we have negative as well. Those are all called integers. So 0, 1, 2, 3, 4, 5, 6, 7 on up. -1, -2, -3, -4, -5 on down. Still no fractions, still no decimals. The next term we have are rational numbers. Rational numbers, I don't like the definition we have here. Rational numbers can be written as the quotient of two integers. So rational numbers can be written as the quotient of two integers. Quotient, we defined what quotient was last time. Remember, quotient means divide. So divide two integers, and integers, remember, don't have any decimals or fractions. So if I can write it as the quotient of two integers, that makes it a rational number. So like 1 divided by 2, 1/2 is a rational number. -3 divided by 5. -3/5 is a rational number. What about the number 7? The number 7. 7, I could write as 7/1, right? So even though 7 we don't usually write as the quotient of two integers, it could be written as the quotient of two integers. 7 is also a rational number. 2/3. 0 could be written as 0 divided by 5 or something like that. Sometimes we have, instead of fractions, we are given a decimal. 1/2, remember, is the same thing as 0.5, right? Or 2/3 is the same thing as 0.6666666 repeated. So sometimes instead of given a fraction, sometimes we're given a decimal and we're asked, is it a rational number? Or is it, well, we'll talk about in a minute, an irrational number? So if it is a decimal, it is rational. You can tell that it's rational if the decimal terminates, that means stops. So like 0.5, it stopped. There's nothing after the 0.5. Or if it repeats. And we said 2/3 was 0.6 repeated. Because it repeats eventually, it is a rational number. So rational numbers can be written as the quotient of two integers. Integers, remember, have no fractions or decimals. They could be positive, they could be negative, they could be 0. We can tell if a decimal, we can tell that a decimal is going to be rational if that decimal either stops or it repeats. So going back to the previous slide, that's kind of what this said here. So fractions and repeating like the 0.6 repeated, or terminating 0.5 decimals. So all of these are examples of rational numbers. So like -2/5, we had that one, not that specific one, but one similar to that on the previous slide. 617, you could write that as 6/17/1. 0, we said we could write that as 0/2. -13. Notice this one here says -3.45878787, and assuming it continues with the pattern there, 87878787, because it eventually repeats, even though the whole thing doesn't repeat, part of it repeats, this would be a rational number. Notice a mixed number we could change to an improper fraction so that it's the quotient of two integers. -9, just like -13 is. 0.234128889, and then it stops. If it stops there and does not continue on forever, then this is also a rational number. So these are all rational numbers. The question then is, what is an irrational number? An irrational number is a number whose decimal part goes on forever, but it never repeats. So it doesn't stop, and it doesn't repeat. And I want you to think about an example of what an irrational number might be. And the most famous one, there it is pi. 3.1415, and a bunch of other stuff. It will never repeat. It never terminates. Roots, a lot of roots are rational or irrational. So like the square root of 2 is irrational. The square root of 3 is irrational. The square root of 5 is irrational. Notice if I look at my calculator and I type in square root of 2 or square root of 3 or square root of 5, 1.4142135662. It looks like it stops, but the calculator only gives me so many decimals. It does continue on forever. And notice I don't see any repeating in here. So the 7th root of 5 is also irrational. There is a number, it's called the natural number. It is E, it's about 2.7. Similar to pi in that it's a constant, but it's irrational as well. It goes on forever and never repeats. And square root of 6, like we talked about these. Notice I didn't say square root of 4. Think about for a minute why square root of 4 might not be irrational. Square root of 4 is 2, because 2 times 2 is 4. And notice 2 is rational. So square roots, if they don't reduce to a specific number, then they are irrational. So the next thing we are going to do is we're going to take each of these numbers and we are going to move them to the innermost circle that they can be classified as a member of. So every single number, the first thing we're going to do is we're going to decide if that number is a rational number or if it is an irrational number. If it's rational, then it might be one of these other ones as well. So let's start with pi. Pi, we just said, goes on forever and never repeats and never terminates. So we are going to put pi in the irrational number. There's also one more irrational number. Let's see if you can find it. And there it is, root 6. That was also on the previous slide, was irrational. Any other irrational ones? Looks like they're all either no fraction or decimal, which means we could write them over 1. Negative 2 over 5 is already written as the quotient of 2 integers. This one could be changed so that it's the quotient of 2 integers. So that's it for the irrational ones. Let's take care of these fractions. Negative 2 over 5. Negative 2 over 5 we said was rational. We want to decide, is it an integer? And remember, integers were no fractions, no decimals, but starting at 0 and going up by 1s and going down by 1s. It's the positives and the negatives, but no fractions or decimals. So negative 2/5 is rational, but it's not an integer, so it goes right in this area. Again, there's one more that would fall under that category. It's right here, 8 and 13/99 is rational, but nothing else. Let's see here, negative 13. Negative 13, it's a rational number. It is an integer, it doesn't have a fraction or a decimal. Is it a whole number? Whole numbers, remember, start at 0 and go up. So it is not a whole number, it's an integer, but no more. 6/17 is rational. It doesn't have a fraction or decimal part, so it isn't it is an integer. It's a whole number. Whole numbers start at 0 and go up. Natural numbers, counting numbers, if I count 1, 2, 3, 4, 5, 6, I'll eventually get to 617. It's a natural number as well. I want you to make a decision on the other ones. We'll talk through them here momentarily. Decide where the other ones belong. The number 1 is a natural number. We can't count. When we count, we would include that, as well as 3 and 23 and 36. Negative 2, rational, integer. It's negative though, so it can't be a whole number. 0 is rational and an integer. It's not negative, but when we count, we don't start with 0. It is a whole number. These should go in your notes. These are true or false questions. And then it wants to know if the statement is false, we need to provide a counterexample. Counterexample is an example that shows it's not always true. So it might sometimes be true, but unless it's always true, we're going to say false. And then we can provide a counterexample by showing at least one example that shows that it's not always true. So number 1 says all decimals are rational numbers. All decimals are rational numbers. You mentioned a couple minutes ago that decimals are rational numbers if one of two things take place. If that decimal either terminates, stops, or if it repeats. Now, all decimals don't terminate or repeat, so this would be a false statement. Pi has a decimal in it, which is about 3.1415. It is an irrational number, though. Number 2 says all negative numbers are integers. All negative numbers are integers. So you try to think, are there any negative numbers that are not integers? Integers, you might recall, are 0, 1, 2, 3, negative 1, negative 2, negative 3. Notice there are negative numbers in between 0 and 1, or between negative 1 and negative 2, and so on. So this one is also false. The counterexample would be negative 1/2. Negative 1/2, it's negative, but it is not an integer. Number 3 says all positive numbers are irrational. All positive numbers are irrational. This is false. We should be able to come up with lots of examples of positive numbers that are not irrational. If they're not irrational, they have to be rational. 6 would be a great counterexample there.